Now it's very clear that neural radiance field, it was like facing like the compute challenge, and that was the motivation for new methods. That was the motivation for new methods. The ideal representation should be, so we were looking for 3D representation techniques that should be fast like meshes. We were looking for implicit 3D representation techniques which should be fast like meshes, continuous like neural fields, differentiable like neural networks, memory efficient, and real-time renderable. Unfortunately, neural radiance field, it satisfies only some of these properties, not all. And hence, we did research and we got something called as 3D Gaussian splatting. So the core philosophy of 3D Gaussian splatting, let us understand the key idea. So in 3D Gaussian splatting, we represent a 3D scene as a set of 3D Gaussians, and these 3D Gaussians are ellipsoid instead of a neural function or mesh. Now see, the idea is very clear. I want to represent a scene in 3D space. I want to represent an object in a 3D space. We call it the 3D representation. So in the explicit representation, I made use of geometries. I combined the geometries to represent a 3D shape or a 3D scene. In neural radiance field, I made use of a neural network which learned a mathematical function, a continuous mathematical function, and that continuous mathematical function, it represented a 3D scene. Now I am going one step ahead. Now I will be making use of 3D Gaussians. Now I'll make use of 3D Gaussians, set of 3D Gaussians. And these set of 3D Gaussians, they, where Gaussian are like ellipsoid. So set of 3D ellipsoids, they will represent the 3D scene. So I'll make use of 3D Gaussians to represent a 3D scene. And each Gaussian, it will store the position. Position will be the center of the uh, splat, the ellipsoid. So the XYZ, the position will be the XYZ coordinate of the splat center in 3D space. Then for orientation and scale, we will make use of a covariance matrix. It will be a 3x3 covariance matrix defining how the splat is stretched, that is the scale, and oriented rotation. So this 3D splat, the position of it, the scale, how it is stretched, and the orientation of it, and the color. And instead of a single RGB color, it stores coefficients that change the color based on the viewing angle, simulating reflection. So it will not just store RGB, rather it will also take into consider the intensity, wherein how the color changes based on the viewing angle. That also is taken care by the color. And the opacity. Opacity means a value between 0 and 1. It determines the transparency of the splat, how transparent the splat is. So now it's very clear that, okay, in 3D Gaussian splatting, in order to represent a 3D scene, we make use of 3D splats, which are ellipsoids, which contain information like the position, which is the center of the ellipsoid, center of the splat, the orientation, the angle, the splat is making, the scale, the color, the intensity, fading, opacity, the transparency, all such kind of information we are storing, like it has been stored by the splat. And like that, millions of splats we have. So the idea is that mathematically we are making use of like a matrix, or some data structure which is containing the information of all these splats, and it will contain millions of records, because every row can correspond to one splat, and that million record sheet, or a data structure is representing a 3D scene. It is representing a 3D scene. So now we invented a new technique of representing a 3D scene, that is the 3D Gaussian splatting. That is the meaning of 3D Gaussian splatting. Now what are the advantages with this technique? Let us understand that. So smooth, continuous representation. Because here, see these splats, they can overlap with each other. And since we are making use of the opacity, we can deal with the overlapping. Because if blue is overlapping green, so the opacity will be very high, like the transparency will be very less. Because green, we want it to be invisible wherever the overlapping is happening. And because of that, no spaces will be there. Unlike in geometry, when we were using the explicit representation, the geometries, there we saw that it was discrete in nature. But here, because of this 3D splats, we have smooth continuous representation. Since it is continuous, we have differentiable parameters, compact storage, because one data structure we can store, because we are just storing numbers. So compact storage, easy projection to image plane, and efficient rasterization. Because now we just have one data structure which is representing a 3D scene. No need for us to render anything. Because in neural network, the problem was that for every pixel, we have to query the neural network and wait for the response. Here, we already have the information. We don't have to wait for anything which will give us the information. We have a data structure which is carrying the information about the 3D scene. So the information for the 3D scene is there with us, and we can just easily make use of it. So real-time rendering is possible with 3D Gaussian splats. So that we will discuss. Now let us see rendering with Gaussian splatting. So see here, no need for ray marching. We don't need ray marching. Instead of ray marching, what we do is that we project Gaussians, that is the splats, onto image plane, and we blend contributions using compositioning, alpha compositing. Now see, I'll tell you what we are doing. See, the idea is that we already have that data structure in place, which is representing a scene. Now, whatever is the camera angle, based on that, we will just project the Gaussians, the 3D splats, whatever information we have for every splat. Based on the camera angle, we can just make use of the information with us and project the Gaussians, like how it will look from a particular unknown camera angle. We'll just project Gaussians onto the image plane. No need for us to query the neural network because information is there with us. And we will project the Gaussians and then we'll blend the contributions using alpha compositing. And hence the result is very clear. It is very fast technique. It is very fast rendering, much faster rendering, and real-time performance is possible. Much faster rendering, real-time performance is possible. Now, why it's a breakthrough? Why it's a breakthrough? 3D Gaussian splatting, it achieves, okay, see, with this technique, 3D Gaussian splatting, we can achieve neural radiance field level visual quality, real-time rendering speeds, and simple optimization pipeline. It's very simple. No ray marching is needed, no need to query, no need for 256 million computation for a normal image. So very less compute is needed. Real-time rendering is possible and very good visual quality we can get. And this is solving a very big problem. And hence it's a breakthrough. It is solving the long standing trade-off between quality and speed. Now it is possible to have good visual quality along with good speed, real-time rendering speed. Okay, so now if we'll just like look at the 3D representation evolution. So now we, like if we talk about the 3D representation, the evolution of it. So it all started with geometry based methods, wherein in 3D scene, we used to represent it with some geometries. We used to combine it. It was accurate, but it was rigid. Then we had neural implicit field, wherein we had neural networks which learned the continuous mathematical function which represented a 3D scene. It was very flexible, but it was slow. Then we had Now we are having Gaussian splatting, wherein we are representing the 3D scene in the form of 3D ellipsoids. We call it the splat. So we have a data structure. It is containing information of all the splat. We can have millions of splat for a scene. And for every splat, there will be a row. It will contain the information like the position of the splat, the color along with the intensity, opacity, the orientation, the scale, all that. So it is like fast and high quality.